This movie describes how to use the transform twice function composition activity. This is one of the geometric functions activities in which students create, manipulate, and experience function concepts by treating geometric transformations as functions using point variables. More information on geometric functions is available here. In this activity, students create two functions and then compose them by merging the independent variable of one to the dependent variable of the other. They use function notation throughout, describe the behavior of the functions, and predict the range for a restricted domain of a particular shape. So let's start the activity. This activity begins with an empty sketch. We have to create everything from scratch. The two functions we're going to use will be a dilation, which will be the dilation will require a center point. Let's call that C. And a translation. The translation will require a vector, and let's label this as the vector that goes from D to E. We'll also need an independent variable. We'll color our independent variable red and label it X. And now we're ready to do our first function. Our first function will be the dilation. We'll dilate by a factor of 2. So there we go, dilated image. We'll color the dilated image differently from the independent variable, and we'll give it its own name, which is going to be the dilation about C by a factor of 2 of X. So now we've given it a proper name, a name that indicates how it was formed. We also need a translation, so another independent variable, let's call this one W, and it will be translated by the vector from point D to point E. So we'll go ahead and translate that. We'll label it as the translation by the vector from D to E of W. And this one we'll label, we'll color rather, green. So let's investigate these two functions. To investigate the first two, I'm going to turn on tracing for those two variables, trace those points, and we get to see the relative rate of change. The dilated image is moving twice as fast and twice as far and making traces that are twice as big as the independent variable. We can similarly see what happens with the translation function. We'll turn on traces for those two variables and then vary the independent variable and see that they move at exactly the same speed and their traces are actually congruent as opposed to the similarity that we see over here. Okay, let's erase the traces and let's go ahead and compose these two functions. To compose them, we'll merge the independent variable of the second function, that's W, to the dependent variable of the first function. So we select those 2 points. From the Edit menu, choose Merge Points, and we have now got the composed function. If I drag X, we get to see X being dilated, that dilation being translated. So we now have those two functions combined in the form of this green point down here as the output. Now, this is labeled with the W, but we don't have W anymore because W is now the dilated output from the first transformation. So I'm going to replace the W by copying the label of the dilation and using it in place of the W right here. So now we can explain question 6 on the worksheet. Why does this label make sense? This green point is the translation from D to E of the dilation about C by a factor of 2 of point X. So that's what this function notation means, and it all makes sense. Okay, we're going to erase the traces and drag to create an interesting shape. Let me do a rectangle, let's say, and I'll finish up right there, and we can see how the intermediate variable moves. We can see how the final variable moves. I don't really need to see this intermediate variable anymore, though, so we're going to hide that point, erase the traces again, and watch the composed function without having to be troubled by that extra variable. So now we're going to take one more step. We will restrict the domain of point X by creating a polygon, which will be our restricted domain. Let's color that to match the variable we're going to merge to it. So by choosing merge point to pentagon, we have now restricted the domain of that variable X, and I can't drag it anywhere except the border of that polygon. So I'll erase the old traces. Let's put this polygon in a bit of a different spot here. In fact, let's surround the center point here and see what happens then. Erase the traces again and animate our point. So now we can analyze the result of the composition. We can determine its relative rate of change, the fixed points, and so forth. I leave those investigations up to you.